Okay, I'm going to go through about half of the problems on your Waves calculations review. Let's start out with number one. A wave's medium vibrates with a period of, so we're just going to choose a number here. I'll do it for you this time. Let's give it a period of 2 seconds. Technically, that would be 2 seconds per cycle. And it has a wavelength of, let's go with 16 meters. So we need to find the velocity of the moving wave, which causes the medium's disturbance. So we want to know what the velocity is. Now, we don't have an equation relating these three variables, but we do have two different equations. So first, let's write down what we know period is equal to. Period is equal to the inverse of frequency. And we know that velocity is equal to frequency multiplied by wavelength. So what we can do is combine these two equations. Now the way that I wrote this one over here, you'll probably see it differently on the board, but I just wanted you to see some more algebraic manipulation to get the hang of it. If I want to solve for frequency, I have to multiply it on both sides. That would give me frequency times period equals 1. And now I want to divide by period on both sides. And that gives me the frequency is equal to the inverse of the period. So now what I can do is, instead of using this equation with frequency, I can plug in the inverse of period for frequency, and it's the same exact equation. It's just solved with all the variables that I'm looking for here. So the velocity is equal to, instead of frequency, we'll write what it's equal to, 1 over the period multiplied by the wavelength. And I can clean this up a little bit more, rewrite it, where wavelength times 1 is wavelength, and divide that by period. So at this point, we're just plugging numbers into our formula. The velocity of this wave is going to be the quotient of 16 meters, because that's our wavelength, divided by our time period, which is 2 seconds per cycle. So 16 divided by 2 is 8, meters divided by seconds, and that's our velocity. So that takes care of the first one on your Waves calculation review. Now the next one I want to do is number 3. Number 3 is a little bit trickier, so let's look at that. A sound wave has a constant speed, and its pitch is changed from, so we need to choose 2 hertz here, from some hertz to another. So we'll say that the initial pitch, and remember pitch is the same as frequency, we'll say that it changes from 5 hertz and we're going to say it changes to, let's say, 15 hertz. So this is the initial, and then we'll choose the final as 15. You could do 1 and 2 instead of initial and final, it doesn't really matter. So 15 hertz is how it ends up. 5 hertz is where it starts out. So if the initial wavelength was measured to be, let's give this 3 meters is our initial wavelength. We want to know what the final wavelength is. Now, we don't have an equation that relates the initial and final frequency and wavelength. But what we do know is that speed of a wave is equal to the product of its frequency and wavelength. And we also know that the initial speed is equal to the final speed. We're told that in the question. This part right here, a sound wave has a constant speed. That right there is the giveaway for how to approach this problem. So I'm going to write the initial frequency times the initial wavelength is equal to the initial speed, and the final speed equals the final frequency multiplied by the final wavelength. So since we know that these two are equal to each other, then we can eliminate them and set these two equal to each other. So the initial frequency multiplied by the initial wavelength has to be equal to the final frequency multiplied by the final wavelength. So we were able to set these equal to each other because we were told that there's a constant speed. So before and after, it hasn't changed, which means it's equal to itself, which means the things that it's equal to are equal to each other. So now if we're solving for the final wavelength, I need to get rid of the final frequency over here. And then we get the equation that we need to solve for our unknown. The final wavelength is equal to the quotient of the product of the initial frequency, the initial wavelength, and the final frequency. Alright, so let's plug our numbers in. The initial frequency was 5 hertz. The initial wavelength is 3 meters. And the final frequency is 15 hertz. So that means our final frequency is going to be, final wavelength. Five times 3, well, this is 1 over second. So technically up top here we have 15 meters per second. That's what happens when you multiply frequency times wavelength. That's why we get a speed value. And over here in the bottom we have divided by 15 hertz. So this hertz down here, 1 over hertz, cancels out with this 1 over, or meters over seconds. So these cancel out with this. 15 divided by 15 is 1, and our final wavelength must be 1 meter. So you see our wavelength went down by a factor of 3. It went from 3 to 1, so it got cut into a third. And that's because our frequency went up from 5 to 15, so it got multiplied by a third. So this shows you the inverse proportionality between these two quantities. Okay, the next one that I think we're going to do is number 6. So a traveling wave moves through a medium blank meters with a frequency of blank hertz. So let's say the medium, or the distance that it travels, let's say that it travels 8 meters. And it has a frequency of let's say 12 hertz. Now the wavelength of this wave is, I'm going to give it a wavelength of, I don't know, 5 meters. And what we want to know is how much time did it take to travel through this distance. So we don't have a formula that relates all four of these, but what we do have is a formula, two formulas for velocity. We know that the velocity of any moving object, as long as it has a constant speed, is the quotient of its distance and time. And we also know that the velocity of a wave is the quotient of its frequency and its wavelength. So since we know that velocity is equal to velocity, we can say that the distance the wave travels divided by the time it took to travel that distance is equal to the frequency of that wave multiplied by its wavelength. This was the answer to the do now question from last week, or it might have been 2 weeks ago. So we're solving for t here. So let me write this down here. The algebra gets a little tricky when you're solving for the value of a variable that's in the denominator of a fraction. The first thing that you're going to want to do is get it out of there. So since it's being divided into t, we multiply by t on both sides. It just moves it over to the other side. Cancels that out. We end up finding that the distance is equal to the product of the frequency, the wavelength, and the time. Now we're looking for the time, so we need to get rid of frequency and wavelength. You could do this in 2 steps by multiplying by each one individually, but we might as well just turn it into 1 step to save ourselves some space and time. So anything divided by itself turns into 1, anything times 1 is itself. We find that the time is going to be equal to the quotient of the distance divided by the frequency multiplied by the wavelength. Okay, I should have chose some larger numbers here. Let's change our distance to 80. Not that it matters to you. So the time is going to be equal to 80 meters, that's our distance, divided by the frequency of 12 hertz multiplied by our wavelength of 5 meters. So it's important to recognize that everything in the denominator here needs to be dealt with first. Otherwise you'll have an arithmetic error if you say 80 divided by 12 and then times 5. So if you're doing this in your calculator, worry about your denominator first and then do the division. So we have 80 meters up top. 12 times 5 is 60. That's going to be 60 meters per second. Our meters cancel out. 8 divided by 6 is 1 and 2/6. Or I'm sorry. Let me see here. One and 1/3. So this is going to be 1 point repeating 3. And then our second, since it's in the denominator of a denominator, it gets brought up top. 1 point repeating 3 seconds. All right, the next one we're going to do is number 7. A sound wave has a constant wavelength. So this is just like number 3, it's just a little bit different. And its speed changes from, let's say that it slows down this time. Let's say the speed changes from 10 meters per second to 6 meters per second. So it changes from 10 meters per second. That means its initial speed is larger than its final speed if it's slowing down. Now if the wave's initial pitch was, I don't know, let's say 2 hertz, 2 cycles per second, then we want to know the final pitch. So this is the initial pitch right here. It's always good to use these subscripts, otherwise it's easy to plug the right number in the wrong place. So we want to know what the final frequency is. All right, so we don't know, or we don't have an equation relating these 4 variables. So what we should just do is start by writing what we do know. We know that the velocity of a wave is the product of its frequency and wavelength. And what we also know is that the initial wavelength is equal to the final wavelength. We're told that in the problem when we read the words constant wavelength. So, just like last time, I'm going to write 2 expressions or 2 equations, figure out a way to eliminate our unknown. So let's say this is the initial, and we also have an expression for the final, or an equation for the final. Now this time it's not so simple. I can't just set this equal to this. First I have to solve for wavelength. So we don't need to do this twice. Let's just do it once and then apply it to both sides. Speed equals frequency times wavelength. Divide by frequency on both sides. That means wavelength is the quotient of the wave's velocity and its frequency. So this is true for both the initial and the final. So I could put an I here and here and here, or I could put an F here and here and here. So what we're going to end up, since we know that the initial is equal to the final, what we can say is that the initial velocity divided by the initial frequency is equal to the final velocity divided by the final frequency. Okay, so now we have everything we need. Let's plug our numbers in. 10 meters. Oh, actually, before we do that, let's finish the algebra over here. We're solving for the final frequency. Since this is in the denominator position, it gets a little tricky. So first things first, get it out of there. Whatever you do to one side, bounce the equation, do it to the other. Alright, so what we get here is that the final frequency is equal to the final velocity equals the final frequency multiplied by the initial velocity, all divided by the the initial frequency. Okay, so there's just we could make this 2 more steps, but let's condense some space and time, make it into 1. I'm trying to get rid of this whole thing right here. Initial velocity divided by initial frequency. So I could divide by this first and then multiply this later, or I could just do it all in one step. So up top, I'm going to write what I'm trying to get rid of, the initial frequency. On bottom, what's going on up top I'm trying to get rid of. That way these 2 cancel out. I have to do it on the other side as well. But let me write that down here. The final frequency is going to be equal to, remember you multiplied by this fraction, so the initial frequency divided by the initial velocity. So I'm just multiplying the same reciprocal of this over here. the initial frequency divided by the initial velocity. Okay, so now we're ready to plug in numbers. Okay, so the final velocity was 6 meters per second. Our initial frequency was 2 hertz. And our final, or initial velocity was 10 meters per second. All right, 6 times 2 is 12. Our meters per second cancel out. We have 12 hertz up top divided by 10 meters per 10, because we already canceled out these units. 12 divided by 10 is 1.2 hertz. So what happened here? Our final frequency was lower, than our initial frequency. But that's because our velocity decreased. So this shows the direct proportionality between frequency and velocity. If one goes down, the other one goes down with it. All right, we're going to do 2 more problems. These next 2 involve the use of an equation that I introduced briefly during your exercises. But first, let's just read the problem. I think we're going to jump to number 8. A string has a tension force with blank newtons pulling on it. All right, so force of tension. We want to use the same letter for force that we have been, F, but we'll give it a subscript of uppercase T, the force of tension. Let's say that it is 20 newtons. And it's, let me bring this up here. Pulling on it, a force of 20 newtons are pulling on a string, and a wave travels through it with a velocity of, I'm going to give it a velocity of 4 meters per second. So I need to calculate the length density of this string. In case you forgot, that symbol, Greek letter, mu, and what it's equal to, well, we're looking for its value, but just so you can be reminded, it's equal to the quotient of the mass and the length. All right, so the formula that we have relating these 3, the velocity of a wave is equal to the square root of the force of tension divided by the mass-length ratio. All right, so if we're trying to solve for this down here, we've got some algebra to take care of. First thing we want to do is get rid of this square root sign by the inverse operation of the square root is taking something to the second power. So we have to do that to both sides. That cancels this out. We see that the square of the velocity is equal to the ratio of the force of tension divided by the mass-length ratio. So we have to get this out of here by multiplying it on both sides. See the mass-length density multiplied by the velocity squared is equal to the force of tension pulling on that string. And then one more step to get rid of that force of tension, or that velocity squared. Okay, so our algebra is taken care of. The mass-length density is equal to the force of tension divided by the velocity squared. Okay, hard part's over. Force of tension is 20 newtons. The square of the velocity. Here's where you have to be careful. Make sure that you put your number in parentheses. Otherwise, you might look at this like it's already, like you're given an acceleration with this exponent next to the second. So 20 newtons divided by 4 times 4 is 16 meters squared divided by seconds squared. Now, I don't really, well, actually, let's do this. A newton is a kilogram times a meter per second squared. What I'm doing is the dimensional analysis right here. Down here we have a meter squared and we have a second squared. So let's look at what cancels out. Our second squared canceled out. This meter cancels out with this square meter, and we're left with kilograms per meter. So 20 divided by 16 reduces to 5/4, which is, I cannot do decimal division tonight, 1.25. So we have kilograms divided by meters, and let's look at our equation, which will be on the board to help remind you. You just have to remember mass is measured in kilograms and length is measured in meters. So our mass length density is 1.25 kilograms per meter. All right, one more, and then the second half is all for you. Let's go to your last problem on this, number 12. It's the same problem, just deals with a little bit more messy algebra, which is the thing that throws a lot of you off. A string has a length of blank meters. So let's give this string a length of, I'm going to say 6 meters. And it has blank newtons of tension pulling on it. So the force of tension acting on this string is going to be equal to, let's say, 12 newtons. And the wave travels through the string, with the velocity of, let's go ahead and say 3 meters per second. Calculate the mass of the string. Okay, so there's two equations here that we're working with. One, the equation for the mass-length ratio. Now we can't solve for the mass of this string until we get mu, or the mass-length density. And we also have the equation for the velocity of a wave traveling through a string with this force of tension acting on it. So first, what we need to do is solve for this variable. Then you could do the math or the arithmetic and then jump to this. I'm going to do all the algebra right away. So first part is exactly what we saw last time. Square this, that cancels out with this. Square the velocity equals the force of tension on the string divided by the mass length ratio of the string. Then we have to multiply by mu on both sides. So the mass length ratio multiplied by the square of the velocity equals the force of tension. This is just a review from the last problem. Not one more step, but one more step to get this alone. Divide by the square of the velocity. If you're feeling like this process is difficult, just practice it. I know it's not something that you probably enjoy doing with your free time, but it will prepare you for the quiz. Just solving for the different variables in these equations will get you ready, because you will have to solve for one of them, depending on which version of the quiz you get. All right, so right now we do have numbers to plug in here to solve for what this is. But I'm going to get done with the algebra right away. Instead of putting mu here, let's put what mu is equal to. It's equal to mass divided by length. And that must equal to the quotient of the force of tension divided by the square of the velocity. So if I want to know what the mass is, I have to get rid of this divided by length. Multiply that on both sides. And that's the final algebraic step. The mass of the string is going to be equal to the product of the force of tension multiplied by the length of the string, and that product is divided by the square of the velocity. I think this is the hardest problem on your quiz, except for, actually the hardest one is where you have to solve for length. So you would get this first over here, and then multiply by this over here, and then divide by this over here. It's the same process that we've already practiced multiple times throughout the year. It's just doing it at the end of what's already a pretty long process. So the force of tension we can plug in now, 12 newtons, multiplied by the length of 6 meters. And then we divide that by the velocity, which is 3 meters per second. But first we're going to need to square this thing. So 12 times 6, let's see, that's 72 Newton meters divided by 3 times 3 is 9 meters squared. Whoa. Meter squared divided by second squared. Alright, so I'm going to spare you the dimensional analysis this time. Look at that, ended up with an integer. This could be one of the questions on your quiz. 72 divided by 9 is 8. I'm not going to do all this for you. Just trust me when I say this cancels out, the meters and up top here cancels out, second squared cancels out, and you're just left with kilograms. Alright, so that takes care of half of your problems. I just did 1, 3, 6, 7, 8, and 12. You need to do 2, 4, 5, 9, 10, and 11. Alright, hopefully this helps you.